Welcome to the Cosmic Pie Podcast, year number four, episode 1. Believe that,
Sorry, I'm
Robert?
going to adjust the camera a little bit.
You believe that now?
I
Fourth
can't.
year.
It doesn't seem like that.
Anyways, I'm your host, Wayne Barkhouse.
And I'm Rob Moore.
Welcome to the Cosmic Pie Podcast. We are broadcasting live here from the University of North Dakota in Grand Forks. We do have a live chat that's running, so if you have any comments or questions that you'd like to ask us throughout the podcast, feel free to do so.
Right.
The other thing I want to mention is we do upload our podcast the next day to Spotify. So if you'd rather listen to us on Spotify or best yet, watch us again.
Yeah, we like that.
Because you miss some things, right? You know, as you watch it once, there's always some details that you miss, and you pick those up on the second iteration.
Right.
As a disclaimer, Robert?
Well, I guess like usual, the opinions and views expressed are those of myself and Wayne. They're not those of the University of North Dakota, the Department of Physics and Astrophysics, or any other entity related to North Dakota or the United States or anywhere else.
Or the
It's
world,
just us.
planet Earth,
Yeah.
the Milky Way galaxy,
And solar system.
our universe,
Yeah.
all that stuff.
Well, it's my universe. You're
Our
late,
universe.
You're late on the rent. Get out.
You sound like somebody else I know who's in power.
Yeah.
We won't go there. That's where they come up with Masters of the Universe.
Right.
Right?
Well, that goes back to a joke. A friend of mine in college, we were roommates, and we got into an argument about how to work a particular physics problem in our intro physics classes, because he was an electrical engineer and I was a physics major. Anyway, he finally is just like, we were ready to go to bed and we were still arguing about it. And he finally was like, look, Rob, this is how we do this problem. That's the way it is. It's my world. It's over. And he clicked out the light. And I look at him and
You just hope there's a parallel universe to go to, right?
there you go.
So how was your break?
It was really good. Went home to visit the family. So that was good. Also did some personal projects and got them lined up. You know about it. But yes, I'm now a published author out there, folks. I've got a book published out there now.
You should have had a slide to advertise it.
Yeah, I should have, but
Next time.
That's not what this is about.
Do it. Don't be shy.
Okay.
How are you going to become a millionaire if you don't publish your product?
I'm probably not going to become a millionaire, but one never knows.
You can always strive towards that goal, right?
Yeah.
If you wait long enough, millionaires will be just like everybody.
Right.
Because everybody be trying to be a trillionaire because of inflation, right? So you have to wait long enough for that, I guess. Now, what about in space? Well, I guess one of the big things that happened near the end of December is that finally we have a NASA administrator, Jared Isaacman. And I noticed he's made a decision already on something.
Which one?
So which one is back? You remember the what is they called? The Big Beautiful Bill or whatever it is?
Right.
That was passed sometime in the fall.
Okay.
So there was money allocated in that bill for NASA to send the Space Shuttle Discovery, which is in the Air and Space Museum in Washington, D.C.,
Right.
to pack it up, send it to Texas. Because Houston wanted it. And the senators in particular thought that, hey, there's so much time and effort invested in the Johnson Space Center here in Houston, we would like to have at least one of the replicas, one of the shuttles, I should say, that actually flew. There's one in California, and there's one at the Kennedy Space Center, the Atlantis, which is the one I visited several years ago and actually got to see it. So these are not just replicas, they're actual space shuttles. And of course, there were two other ones which got destroyed. The Challenger first and then the Columbia. So anyways, there was money allocated to move. And of course, the National Air and Space Museum was like, no, we have a contract that we signed, essentially where NASA gave us, or we bought in some way, if you want to think of it that way, the space shuttle for us to display forever here. In fact, that's our thing, is we display, aerospace-related things.
And I agree with
models
that.
or the real thing, right? So there was a bit of a controversy what's going to happen. And I guess what Isaacman had done, Jared, is he looked at the cost of how much it would take to pack up the shuttle and move it to Texas. In fact, the airplanes, no longer, they've been mothballed and stored away, so you can't use them.
Right.
So really there is no good way of getting the Discovery to Texas without taking it apart. And once you start taking it apart, you can destroy it.
Right.
So you no longer have the original shuttle, right? You'd have to repair it and it would be the same. So what he decided, this is the decision he made, is we're not going to do that, even though the money's in the bill that was passed, right, allocated by Congress. In fact, it's not enough money.
Right.
Somebody actually did the figures and said it's going to take a lot more than what they provided. So it's going to cost American taxpayer probably well over $100 million to do the move. Okay. So what NASA administrators said is, we have Artemis 2, 3, 4, and 5, and 6 coming at some point, or whatever the number is, right? Certainly Artemis 2 is supposed to be launched this year. So this could be a big year for going back to the moon. We're not going to land on the moon, but we're going to have human beings, 3 Americans, 1 Canadian, that is going to go in a loop around the moon and then come back. So they're testing all of the life support systems, which were not tested before because they sent up Artemis 1 a couple years ago, but there was no one on board, and some of the life support system was not required, therefore wasn't there, so they couldn't test it fairly. So a lot of things are going to be tested, including the heat shield. We can go into that a little bit here in a second, what that means. But what do you do with the spacecraft once you're finished with it, Artemis 2? I mean, you've got to put it on display usually somewhere.
I was about to say they're not reusable. So
No, and so that's what the NASA administrator is suggesting, that we can give them the Artemis 2 spacecraft.
Okay.
Or Artemis 3, the one that will land and stuff and then return eventually. Whatever one they want, essentially, they'll probably get. And that's a lot easier to do that. And plus, if you just give the Discovery to Houston, how are they going to display it? They got to spend all this money to build some kind of a building to surround it, to protect it from the elements.
There you go.
In fact, I went to the Johnson Space Center a few years back. This was just before COVID, if I remember right. And they have a static display of a Saturn V. It's laying horizontally, not vertically. And it's in a building, so it's protected from the elements. So you can actually go in and see a real Saturn V.
Right.
Because when the Apollo program ended with Apollo 17, there were actually 3 more Saturn V's that were built because they were expecting Apollo 18, Apollo 19, and Apollo 20.
Yes.
And they canceled that because of budget cutbacks, unfortunately. We could have benefited from those other 3 missions in terms of geology, especially.
In terms of the geology, because we started learning what we were looking for.
Yeah. So one of the Saturn V's was used to put Skylab in orbit in the 70s. Another one is on display at the Kennedy Space Center, and then, of course, the third one at the Johnson Space Center in Houston, Texas.
Right.
And so you have to build some kind of an infrastructure to support these displays. So that's going to cost money. There's a lot of money. You can't do anything in this life without costing money, it seems, right? So it's either way, it's going to cost more money than what was budgeted for. So, all things considered, this is probably the best way to do a compromise.
Right.
So hopefully everybody's happy with this. But that was his first
they won't
real.
be, but that's beside the point.
That's his first real executive decision.
Okay.
Okay.
Well, I agree with that one.
Yeah. Now, going back to the moon is interesting. Number one, there was some talk about the heat shield. This one, again, one for the Artemis spacecraft on its return. And some people suggested that the heat shield is not up to snuff like it should be.
How do they mess that up? We've been doing that since the 60s.
Well, you're always trying to use new technology, aren't you? You're not always trying to use 60. I mean, we had test tubes for how many years, right? I should say, tubes, electronic tubes I'm getting at, right?
Okay.
So it's not like you're going to rip out the transistor when it was first developed and said, well, why bother with that? We'll use the true thing we've been working for years now with tubes, vacuum tubes.
Right.
Right. Well, let's put them in electronic circuits. Well, no, the transistor is way cheaper, way better, more efficient. Let's learn how to use transistors, right?
Right.
So it's always, development on anything, right? It's always, human beings always want to do the same thing over and over, and they're really resistant to change.
Yeah.
Right? To adopt new things.
I got to admit, if something works, you look at improving it, but, in the end, if you can't get something to work in time, you go with what works,
And don't forget, there's a time gap, though, between the Apollo project and Artemis. And that time gap was filled by the space shuttle with different technology in terms of the heat shield. We went to the ceramic tile system rather than the ablative type of heat shield, where material peels off the bottom of the Apollo capsule, and that dissipates the heat with the tearing of that material.
Right.
And you have enough material layers of it that you get to the cooler part of the atmosphere, right? You get out of the high heat before the heat shield is totally ablated away and it starts tearing away the main craft and there punches a hole through the spacecraft, right? So that's the idea. And the same kind of thing here. And of course, you want to try new technology, something better, maybe.
Better
advancement
ceramics,
of material,
okay,
so on and so forth.
So it's lighter.
But my
thinner.
my understanding is that the heat shield did not perform as they expected in Artemis 1.
Okay.
So some people suggest we should set up Artemis 2, but have it also unmanned. And maybe we can check out, number one, all of the life support system that wasn't in Artemis 1. We'll have it for Artemis 2. And plus, we can check the heat shield as well. But of course, that costs a lot of money. You know, the SLS, well, I guess that's the space shuttle, but the Artemis, right? The Artemis rocket is a lot of money. It's like $1 billion or something like that. Right. I don't know if it could be $1.5 billion for all we really know if you add up all the money, right, the support. And it's taken them several years to build to get it ready. Of course, that time will go down once you start building them. If you had the money and you could say, okay, we need 20 of these things over the next 20 years or so, they could do it, right?
They could do it. The economy of scale starts.
Yeah, exactly. And so maybe we should have tested one before we send people on it. But that costs money, and they didn't want to do that. And I think a lot of people probably also looks at the fact there's some pressure a little bit because China has stated they are going to go to the moon probably by 2030.
Right.
So here we are now, obviously in 2026. That's only 4 years away. So if we're going to beat China back to the moon, I mean, this is a space race. We got to beat China we already beat them in the 60s.
Right.
Why do we got to keep beating them?
We don't need to beat them again.
Why do we got to keep beating other countries to the moon? We already done this. Right. And of course, all missions were stopped at Apollo 17, the human flights. So humans to go back to the moon, then they're going to use Artemis 2. And that's the window of opening is around February the 5th.
Okay.
So if you have time to go to Florida for a couple of days starting in February to see the launch, it would be a fantastic type of thing. So if anyone out there would like to see a launch, this is like one of the biggest rockets we've ever built.
Right.
With humans on board,
With humans on board.
To be launched. It's even more powerful than the Saturn V. That's the launch to go to. And if my understanding, they're going to be launching it at night as well. So you're going to get a really cool view of the liftoff. It should be fantastic. Anyways, not all of us are fortunate enough to be able to go at a notice. And you know what would happen if I did that?
It'd be cloudy and scrubbed.
Yes, exactly. And and then I'd go home empty-handed after spending the money to go there and the time. And you never. So that's the problem. If you lived in Florida near that area, of course, it's easy.
Right.
Or easier, anyways, to get to one of these things. But we'll see what happens. But yeah, so they're going to be launched. And some people suggest that maybe it'll be like March or April. It could be during spring break for us. I don't know. But like I said, you go there and I think gets scrubbed 2 seconds before launch, and then they got to take some month to turn it, and then you lose your chance.
Yeah, because you can't just leave it standing up there. You got to bring it back in, tear it down.
All that. And then the thing for us, though, living in North Dakota, if we do go to Florida in February, we get the added advantage that even if the flight does not happen, we can run to the beach.
Yeah.
You try doing that around here, running to the lake in February, and
I hope you brought your ice skates.
You'll be ice fishing or something. I guess you could do that. But anyway, so we'll see how that turns out. So yeah, it's a big year for human exploration of space and going back to the moon. So it's going to be interesting how all that plays out. Hopefully, of course, everything works, and then it's a matter of just finishing up the design of a lander, so that we can eventually launch Artemis 3, which is supposed to be landing on the moon.
Hint, nudge, Boeing and SpaceX.
Well, yeah, people and Blue Origin.
Blue Origin? Okay.
Blue Origin and SpaceX are their sort of primary.
Oh, okay. I thought Boeing was in that too.
No, we won't get into Boeing, but they have had a lot of problems lately. You might have noticed.
Yes.
I don't know if you want to. I don't know if you wanted to ride a lander from moon, lunar orbit to the surface of the moon in a Boeing-made vehicle right now. I'd be like, okay, you go first, and if it works,
then I'll follow you.
Send it back up, and then I'll come down. That kind of thing. Anyways, so that's that. But there was a lot of talk last year, since July, of course, about one particular object. If you want to show the first slide here. And that's, of course, Comet 3I Atlas. You got kind of get tired of talking about it.
Right.
But, it takes a while to write the research papers to get the results out. And I thought this was kind of interesting. So this is a paper that has been submitted day after Christmas in Canada. We call Boxing Day in UK.
Yep.
Not in the United States.
Isn't that
of
where
course.
people switch roles or something?
That's when you take all your stuff back to the store because it didn't fit. Like,
So it's not unboxing day.
yeah. You box it up and take it back to the
Got it,
store.
okay.
That's Boxing Day. This doesn't fit. My great uncle bought me a sweater. How much money? Can I get the money for it instead?
Yeah.
I just don't want another sweater because it's ugly. I'd rather have the money. Anyway, so this is a paper that has been submitted. It hasn't been published. So it hasn't been peer reviewed. So take that with a grain of salt. Okay?
Right.
And what it is a paper based on observations taken from the SOHO spacecraft. And the SOHO spacecraft's been up there for a long time, several decades now. It's one of our primary observer of the sun to keep an eye on the activity of the sun itself. And that would include things like solar flares that people hear about, or maybe they don't hear about these sort of other events known as coronal mass ejections.
Yep.
And we need something to keep an eye on the sun because the sun is not a static sort of bland object. It is extremely active and dynamic.
Especially right now.
And the sun goes through this 11-year solar cycle where there are times where it's very energetic and other times not so. And during the time of increased activity, you have a lot more of these sunspots that you can see at any given time, these magnetic storms on the photosphere of the sun itself. And so we like to keep an eye on it. Number one is because we have a lot of technology that can be impacted by the sun. And I mean, like satellites in Earth orbit. And a lot of them, depending on how high up they are, they can feel the brunt of any type of high energy particles that stream off the sun and eventually reach the Earth.
Yeah.
And they can be impacted in terms of their electronics can be short-circuited and then the satellites can be destroyed. A lot of these satellites are important things, like weather, but even military satellites. So we're always very careful of trying to make satellites that can stand up to these sort of conditions. And we need to monitor things because if we can give even a few minutes notice that there's a large event that happened on the sun, like a solar flare, and these high stream particles are on their way and will get here, they travel, the particles themselves, less than the speed of light. So it may take them, a day or two to get here, that maybe we could do things with our satellites, like even turn them off to protect them.
Right.
And then reboot them back up again once the storm sort of subsides. So
that is the plan.
That is the plan. That's known as space weather. And so there's a lot of money now invested in this type of thing. So that's all part of this understanding the Earth-Sun system, if you like, and keep an eye on the sun itself. So SOHO is in this L1 position. That's the stable position between the Earth and the sun as it orbits the sun at the same rate that the Earth orbits the sun.
Right.
And one of the things it has on board is this camera, this detector, known as SWAN. So this stands for Solar Wind Anisotropy All-Sky Hydrogen Lyman Alpha Camera. That's a mouthful. No wonder they call it SWAN. That's a much easier way of seeing it. And in fact, you can see there's an illustration of SOHO on the right side and a nice red arrow, in case you're colorblind, pointed to the SWAN detector itself. So that's where it's located. Now, when Comet 3I Atlas made its closest approach to the sun, which is kind of a misnomer because it was still quite a distance away from the sun.
It was still out past Mars' orbit.
Yeah, it was like 1.4 AU or so, roughly. And where 1 AU is the average distance from the Earth to the sun. So it was about 1.5 times the distance from the Earth to the sun at its closest distance to the sun. They turned that detector towards the comet, and one of the things it can measure is hydrogen coming from different objects, like our sun.
Right.
And what it detected was hydrogen associated for water being broken up by the ultraviolet light from the sun itself.
Dissociated, right.
So water, as you probably know, in the molecules of water is 2 hydrogen atoms for every oxygen atom, H2O. And so if you take the water and break it apart into the individual atoms, 2/3 of it is going to be hydrogen.
Right.
And they were able to detect the amount of hydrogen coming off the Comet 3I Atlas. And from that, they were able to calculate what is essentially the sublimation rate, how much water is coming off the surface, assuming, of course, that it's coming from water from the surface of the comet itself is what they're seeing. And all indications point to that. There's no evidence that go against that. And so you can get then an idea of what is this sort of water production rate as you see on this slide, which is plotted here on the y-axis, the vertical axis. And on the x-axis is the time since the closest approach to the sun. This is the time in days, as you see. And the closest approach is the perihelion part of your orbit. And you can see that the water production rate was quite high within 10 days after the closest approach to the sun. And then you see this kind of drop, right? Dramatic drop, on order of a magnitude, roughly, drop in the production rate as we get further and further, beyond that closest approach to the sun. Now, one of the things we like to do is you take the Comet 3i Atlas and you want to compare it to other comets that exist in our solar system. And when you do that, you notice that the amount of water that's sublimated off the surface of the comet would indicate that the coverage of the area of the comet itself, the nuclei, and we're not quite sure how large it is, okay, but it indicates that roughly water came off about an area equal to about 20% the area of the comet itself. Now you may say, okay, big deal, what do I do with that number? Well, you want to compare it to other comets that you know about. As far as we can tell, most normal comets in our solar system, the water coming off of those, so-called water coming off a comet, is not unusual. We observe it many times in the past before from other comets. Is only order of 2 to 3% of the area.
Okay.
Which,
that is weird.
Well, it's weird in the sense that why does a larger percent of the surface, and could be up 10 times more, right? Why does a larger percent of the surface of Comet 3i Atlas have water sublimating off of it compared to the solar system comets? And one way you can think about it is what happens, and we use this argument a lot for why the observations show there are some properties of this comet in particular that's unusual, not the average, that are a little bit different. What happens if this is the first time this comet has passed near a star, close enough to the star, that it feels essentially the impact of the ultraviolet photons coming from the sun that disassociates the water?
Right.
So a lot of the comets, have gone by the sun that are in our solar system, have gone by the sun many, many times. Now, their orbits could be 10,000 years.
Right.
But they've been around for 4.5 billion years. They've gone around, you can do the math, many, 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 many times. So over that time, a lot of the water from the comet has already evaporated off the surface. So there's a lot less of it. There's probably fresh supply that comes from cracks or crevices in the comet's surface, and that bleaches up to the surface. And then on the next close approach of the sun in their orbits, then they release that water, but then it's only from a very small area, 2 to 3%. But if this Comet 3i Atlas, which is an interstellar comet, is its first time getting near a star, or very few times, then you'd expect, wouldn't you, that there's going to be a lot more area covered by water that will be sublimed off the surface.
I guess we're back to the whole point that it'll be interesting to see what comes out, because I'm betting that we're going to start noticing a lot more of these things. The technology and the observing capabilities have gotten where we can notice them. So I think we're going to start seeing a lot more and see if this is normal behavior for exactly what you're saying.
Now, if it was urine coming off the surface, then we could say it was a spaceship and people were dumping their waste out into space.
Yeah.
So you need evidence for that, right?
Right.
And it's not a joke, because I'm saying if this is an alien spacecraft, which some people have speculated as we've gone into ad nausea over the past several months, that we should see some evidence eventually that would indicate that. And there's absolutely no evidence of that.
Right. Are there anomalies? Yes, but it's still perfectly normal cometary behavior.
And it is especially for a comet that maybe hasn't gone by
a star.
Yeah. You would expect all these things. So anyways, then the comet, of course, made its closest approach a couple months ago now.
And now it's way on out there.
Yeah,
it was screaming. It was fast.
It's on its way out of our solar system, never to return, of course, unless there's some life form that intervenes.
Right.
We'll just leave it at that.
We'll leave it at that. We'll see if it happens. If it does,
we will see.
Great.
Okay, speaking about a runaway comet, we have a runaway black hole on our hands.
And not just any black hole. This is a supermassive.
Supermassive. What do we mean by supermassive? Well, you can actually divide black holes into sort of three main categories. Well, four if you want to get technical. The fourth one we haven't actually seen yet. Number one are these so-called stellar mass black holes. So these are black holes that would form from, let's say, the core collapse of a massive star at the end of their lives when it goes supernova. And after it goes through supernova, if the mass of the central nugget that's left over has a mass, we think, greater than roughly about 3 solar masses, it'll collapse down and form a black hole. And of course, the mass of that black hole, if it came from a massive star, could be 3, 4, 5, 10, 15, 20, 40, 60. In fact, we have a better idea of the masses of those type of black holes from LIGO, the gravitational wave detection. And so we do see, masses on the order of tens of solar masses. So that's not unusual in that sense. So those we refer to as stellar mass type black holes. The other type of black holes is what we call the so-called intermediate mass black holes. And you're talking masses of many thousands, 10,000, let's say even 100,000 solar masses. And there's some evidence for that. And we're getting better and better data all the time, so that will only increase more of these type of candidates for these so-called intermediate mass black holes. The interesting thing is, of course, how do they form? We don't quite know how they form. Could be mergers of other black holes, like really massive black holes of hundreds of solar masses that merge together, and maybe several of them. They're in clusters of stars, massive stars early on, and you can build up to mass to thousands of solar masses. But it's one of those avenues of research that people are still working on, so we don't really know, exactly the details of how they formed. And then the third category are these so-called supermassive black holes. There's one in the center of our own Milky Way. It's about 4 million times the mass of our sun. And there are other supermassive black holes that are billions of times the mass of our sun. How do they form? And we don't really know how they form. I mean, people are working on those ideas.
That's one of the missions of JWST.
Yeah.
Try to work on that.
And it's not like you can take a bunch of stellar mass black holes and jam them together, because you could get up to thousands, but we're talking billions in some cases.
Right.
So it's like you almost have, a primordial cloud of material that somehow has very little angular momentum, no rotation or very little, and it somehow is able under the right conditions to collapse down. And instead of forming a massive star, it goes right to the black hole stage and forms these giant black holes.
Right.
And maybe they're of tens to hundreds of thousands of solar masses or more, and then they merge together, a bunch of them that form, and then you're up into millions of solar masses. I mean, who knows, right? We're still a lot of speculation about how this occurs.
Right.
And in the fourth category are these so-called primordial black holes, and these are ones we haven't seen yet.
Oh, okay.
So under the very high density conditions in the very early universe, we expect that extreme sort of events happen where you have a really high density region of material, and that's high enough that it can collapse down to form these really tiny black holes in terms of their mass. And these are the so-called primordial black holes. We've looked for them, haven't found any, and we're still looking. You can work out theoretically what is the signature of these black holes. They have so little mass that for a black hole, one of the things we discover, and this is work that Stephen Hawking did many years ago, is that they essentially evaporate in this Hawking radiation that they emit. And if they have very small masses, this evaporation happens fast. If they have large masses, it happens extremely slow, many, 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 many times the age of the present universe.
Right.
But for these really, really small little nuggets, if you like, that were formed in the very early universe, then we should at least detect them, some of them, evaporating away. And the signature of that evaporation will be noticeable. We should see it burst.
Gamma rays, if I'm remembering correctly, of a very specific frequency.
Right, and very specific spectrum.
Yeah.
And we've looked for these things. In fact, we see sources of gamma rays, flashes of gamma ray bursts. They were discovered, back in probably the 60s with military spacecraft, first of all. Anyways, but they don't have the right spectrum to be these evaporating black holes, so they can't be them. In fact, most of the gamma ray bursts are associated with supernovae. In fact, these magnetars really very strong magnetic fields associated
we're
with
realizing
these.
some neutron star mergers and things like that.
Right. And so we haven't seen any evidence for these primordial black holes, although we've looked for them. And some people invoke them as a way of explaining the so-called dark matter in the universe. And if you're not familiar with dark matter, it's when we look at objects that we can see, objects that emit light like ordinary stars or clouds of gas like hydrogen gas, for example, we can measure how they move in response to the gravitational field that they're embedded in. And then we can look at the sources that are responsible for that gravitational field and find that we don't have enough mass.
Right.
That we need another component, some other matter that has gravity that combined with the ordinary matter that we can see is causing things to move the way we observe them to move.
To put it in a little different perspective, the stars at the edge of our own galaxy, the Milky Way, for the amount of mass that the Milky Way we can observe in the Milky Way, they should be flying off into deep space. The Milky Way does not have enough visible matter to hold on to them.
Yes.
At the speeds they are going.
So in other words, the objects are traveling faster than the local speed limit.
Right.
You can think of it that way. And it's not just that. Those are called rotation curves that we can... It's not just that. We see evidence for dark matter in a different circumstance as well. For example, we know it's the combined influence of all the matter, whether it's dark or not, that causes a warpage of space and time to be complete. And we can see these so-called gravitational lensing features. And those lensing features then occur because of the warped nature of space-time, and that's due to all of the mass. And when we look at these lens feature and then look at the objects that we can see and look at their masses, we find there's not enough.
There's not
You
enough
need
visible matter.
you need
Right.
5 times more matter that you can't see in that area, region of space, to reproduce those gravitational lenses.
Right.
So it's another evidence for dark matter. And you can analyze the leftover heat from the Big Bang, the cosmic microwave background. That points for evidence of dark matter. In other words, there are many independent observations that you can do looking at totally different things that all point to the fact that you need dark matter.
And what finally convinced me is you mentioned that factor of 5. They all also point to a factor of 5, roughly, not enough matter.
Exactly.
So it's like you've got several avenues that are completely independent of each other, pointing to the same amount of missing matter. Chances are something's going on,
And the biggest question, really, if you were like a young graduate student and you wanted to put your time and effort in something that may pay off big in the future, is not if dark matter exists, but what is it?
What is it?
So put your time into figuring that out. And right now, most of the things people are looking at involve some, subatomic particle or particles, plural, that we didn't know existed before, that really don't interact with anything except via gravity. And people say, well, that's very strange. Why don't they emit light? Why don't they absorb light? Why don't they reflect light? Well, we have particles already that we know that exist. We've detected them many, many times. These are called neutrinos.
Right.
And neutrinos essentially don't interact with anything except via gravity. And that's why they can travel through, blocks of lead that are light years in length, if we had such a thing, with the probability still being low of any type of interaction. So they're very, very elusive in that way, very hard to detect. But we have the technology we can detect. In fact, we'll say more about that later,
in a little bit.
later on in the podcast. So this sort of study then is looking at a black hole that is really... It is the fastest moving black hole that's been confirmed. You can see how fast it's moving, over 2 million miles per hour. So roughly about 1,000 kilometers per second. So it's really going, like it's really scooting along.
And when I see speeds like that, I'm going, what kicked it up that high?
That is the major question. So if you go to the next slide, we can see sort of a better idea of why we know it exists. So in this case, this is a Hubble Space Telescope image. It was discovered, this object, a couple of years ago, and then recently there's been follow-up observations with the James Webb Space Telescope. And what you see there is that horizontal band or finger-like structure, sort of in the middle of the image. That's the wake that's produced by the black hole that's moving to the right in this image that you see here. And so if you go to the very end of the wake itself, it's underneath essentially the galaxy that's labeled Z equals 0.464. That's the redshift of that particular galaxy. That at the very beginning of that wake, then, that's where that supermassive black hole resides. And you can see the yellow boxes there. Notice they're essentially centered on the end of the wake because they're doing follow-up observations of the black hole itself. And the galaxy that it was kicked out of is the one that's on the far left. Z equals 0.964. So that's its redshift.
Wow.
And his arrow pointing to it. So it came from that galaxy. And knowing the distance to the galaxy and how long that wake tail or structure is, you can measure in physical units how long it is. So it's about 62 kiloparsecs long. Now, what's a parsec? Well, it's a unit of distance we use in astronomy. It's equivalent, 1 parsec, to about 3.26 light years, okay? And what's a light year? Well, that's the distance that light travels in 1 year. So if you convert it to light years, which might be a better way of thinking, it was over 200,000 light years in length. So
I'm sitting here thinking this is a supermassive black hole of what, 10 to the 7th?
Yeah.
So that's tens of millions of
10
solar
million,
masses.
10 million solar masses roughly.
So it moving that fast is really just more or less tearing through space-time, isn't it?
It is. In fact, you don't want to be in a galaxy that's in the way.
Oh, heck no.
For sure. So it's neat when you think about it. Yeah, so the mass of it is about 10 to the 7 solar masses. And if you go to the next slide, Robert, you'll see this is the James Webb Space Telescope observation. So this is using NIRSpec to look in details of the spectrum of the top panel is of the center object where the black hole lies. And if you look at the spectrum, you can see different emission lines. And you got emission lines from oxygen and from hydrogen and sulfur. And then if you look in the middle panel, notice that the color image you see there sort of on the right shows you two horizontal white line, two vertical white lines. And that's the slit of the spectrum. And so it's covering now the knot in the wake. And you can see the makeup of the emission lines from that. And then if you look at the bottom panel, notice the slits are more towards the left. So it's a knot of a gas that's further away from where the black hole lies. And from there, you can tell there's a lot of enhanced star formation occurring in this gas. So gas has been ionized, and the gas has been compressed, triggering star formation. But
that's kind of crazy.
It is. And that gas is itself traveling at hundreds of kilometers per second. But if you look at the next slide, you can actually get the detail now, what's happening at the very beginning of the wake where the black hole lies. And you can actually see a bow-like, a structure.
A bow shock, yeah.
A bow shock. So caused by the high-speed movement of the black hole running through the ambient material around it.
Right.
Producing this wake-like feature. And all of the characteristics you'd think of a speedboat going through the water and you have the bow shock. In front you see the ripples peel back. Or you think of an airplane that's traveling faster than Mach 1 in the atmosphere and you get that sonic boom effect. Right? This is essentially what's happening here. You get that sort of wake, right? The shock front that's at the very front of the object itself. And you get the disturbance then that lies behind it. So all of the information, these observations, what we get is that it supports the idea it is this bow shock sort of feature. So it's consistent with the fact that we do have an object that's moving at an extreme speed towards the right and the way this is projected here. So it is all consistent with that. The big question, of course, which is at the bottom, is how was the supermassive black hole ejected? You're talking about 10 million solar masses. It takes a lot of oomph to get this thing moving in terms of the inertia.
It had to have been orbiting or in conjunction with an even larger supermassive black hole. Wouldn't that be what it takes?
Well, here's the two main ideas that the authors suggest in their paper. Number one, it was ejected through galaxy merger. And what happens is you have the objects in this, like almost every galaxy we know of has a black hole at its center. So if two galaxies merge with each other, ultimately those two black holes may come within close proximity. And we know black holes merge. We detect the gravitational waves from that through LIGO. And one of the things can happen is you get a burst of gravitational waves being released. And the author suggests that this is a propulsion type of way of pushing the black hole off to one side.
Okay.
If you get like asymmetric type of merging occurring.
Right.
So I don't know if that
I can
that's
see
a suggestion.
but I'm...
Yeah. The other one is that some galaxies have more than one supermassive black hole near their centers. Some of them would have two. So you could get two black holes then that come in close proximity to a third black hole that's in the second galaxy if they merged. And you have your three-body problem where due to orbital mechanics, one of the objects can be ejected from the system.
Right.
So that would be that this black hole got ejected and the gravitational interaction with the other two black holes.
And I would lean more that way, but I've worked more with planets and stellar stuff, which is what happens there. So
yeah, so it's very interesting. And of course, people will do follow-up work, and when we get larger telescopes and stuff, to be able to help them unravel this sort of mystery of how this object was ejected from that location with such a high speed.
Now, it's not coming at us, right?
It's not coming out. It's very far away, so we don't have to ever worry about this type of object.
Okay.
But the authors do mention the fact that if there was a galaxy in the way,
be like bowling pins in front of a 50-pound bowling ball.
Yeah, it would be it'd be like a huge projectile ripping through your house.
Right.
Like it would just destroy everything. So that would cause, a lot of cosmic sort of upheaval if you happen to live in that galaxy. Thankfully, there's none around us that we are aware of, so we don't have to worry about that. Now, going closer to home.
Closer to home.
Our friend, Betelgeuse. Just don't say it 3 times in a row.
Right.
One of the things that occurred recently was the discovery a couple of years ago that Betelgeuse actually has a companion star.
Mm-hmm.
So Betelgeuse and the companion star are sort of in orbit around the center of mass of the system. It's very hard to detect that because normally if you look through a telescope at some star that looks like a single star with your eye and you see 2 stars really close together, and if you watch them for a while, of course, what astronomers would do is they measure their shift of their spectral lines to see how fast they're moving and how far away they are from each other. You can estimate what is the separation in physical units, kilometers or whatever, that you can tell they're in orbit around each other and not just chance projections on the sky. So when we look at Betelgeuse, we see a single star. And the reason we've always seen a single star up until recently is because the companion star actually orbits inside of the chromosphere of Betelgeuse, inside of its atmosphere.
Inside of its atmosphere.
And its atmosphere is tenuous enough, diffuse enough, that it doesn't destroy, on short time scales, the companion star.
On long time scales, it will.
Well, we have evidence of that in this study.
Yeah.
So the companion, which unofficially, I don't think the IAU, the International Astronomical Unit, has officially named this companion star, but people are using the name Sawara.
Sawara?
Sawara. They always pick names I can't pronounce. When they call like John or Smith, Henry, Adam.
You know what?
Object A.
Betelgeuse B.
Object B.
Betelgeuse B.
Yeah, exactly. So anyways, this study actually uses speckle interferometry observations that allow us to compensate for the blurring effect of Earth's atmosphere to actually detect a wake in the atmosphere of Betelgeuse produced by the orbital motion of the companion star. So if you go to the second slide, you actually see variations, if you like, of the spectral lines, both their equivalent widths, which is the strength of the line, and their radial velocity, so the movement of things. And you have in the center there the sort of vertical band, the gray band, that's during the time of eclipse. And then on either side of that time outside of eclipse, before going into the eclipse, and after egress type of thing, ingress and egress. And if you go to the next slide, you actually get an artist's conception of what we think is going on here. And so the dashed blue circle is the one that is the orbit of the companion star. And notice that the companion star has a lot less mass than Betelgeuse. So the barycenter, or the center of mass,
is much closer to Betelgeuse.
It's near the center of the center of Betelgeuse itself.
Right.
And what we see here is what we think is that explains the changing in the spectral lines is that there's a wake produced in the outer atmosphere of Betelgeuse due to the motion then of this companion star. And you would expect that if that indeed was the case, if it's real. And so the interesting thing is all evidence suggests that indeed there is a companion star to Betelgeuse, which is amazing.
Right.
And in the sense that it hasn't been evaporated away and destroyed. And the other thing is, it's on a short leash.
2,000-day period.
Why?
Yeah.
No, I mean, why is it on a short leash in terms of its existence?
Oh, because Betelgeuse is about to go supernova.
Yeah, if you looked around in the northern hemisphere and say, name me a star that's ready to go supernova, which star would be near the top of your list?
Betelgeuse. It's an astronomically speaking in any day now type proposition on that one. So, but it's my understanding also that, and this goes into how short the lifespans of Oka type stars like Betelgeuse are, is that companion Sawara is actually an A class, a very massive star itself, but it's still pre-main sequence.
Yeah.
So we're talking about a massive star that only lives for a few million years itself, and it's not even reached main sequence, and Betelgeuse is about to die.
Yeah.
So that's how much shorter the lives of these massive Oak-type stars are.
And when Betelgeuse does go core collapse supernova and blows up, it's going to destroy anything near it.
Anything near it.
Like this star. So if there were any planets,
they're gone.
They're
already gone anyway.
Yeah, they'd probably be destroyed by just having the star orbiting inside the outer atmosphere of Betelgeuse.
Star. Yeah.
And they may not even have formed to begin with, right? Conditions were such that it went against the formation of planet. And so you're not going to have life. So you're not going to worry about, being on this planet thinking, oh my God, it's going to go supernova anytime. We got to move.
It's a pre-industrial civilization.
Yeah, that Earth over there 500 light years away looks a lot better to us now than it did. But yeah. And so you always wonder, what are the conditions when you see a star blow up like that? How far away does another companion star have to be with potentially a system of planets that it survives the supernova explosion?
And people are doing calculations on that.
And that would depend on a lot of things, of course. But if there's life, on some planet, and that star is a lot older than the other star, so there's a huge difference in formation, and the other star, eventually formed, and it was a lot more massive, so it had a shorter life, and so it becomes near the end stage of its life, ready to go supernova, where the other star is a couple billion years old, let's say, with life that has might not be intelligent, maybe bacteria type of life, or amoebas wandering around or something. But yeah, you figured that would be a harsh environment to live in if a supernova went off nearby. And we know that's the case. You want to say something about the evidence of the fact that there has been supernova that went off near our sun?
Oh, yeah. And that's due to the fact of the presence of certain short-lived radioactive isotopes like aluminum-26, and I think it's hafnium, a radioactive isotope of hafnium that decays to tungsten. And these are created in the core, the neighborhood, the vicinity of a supernova. They exist inside our solar system. They exist here on Earth. So there was supernova, at least one, that went off near where Earth and the sun were forming back in the very beginning of the solar system.
Yeah, so we see direct evidence of this. Only way to explain the observation of these isotopes of aluminum, for example.
Otherwise they wouldn't be there.
Yeah. So that's interesting. In fact, one of the ways of forming a star, and it may or may not have been the case for our sun, is that if you have a supernova go off, the shock wave produced in that explosion can compress material and ultimately trigger things to allow the formation of a star through gravitational collapse.
Right.
So that may or may not have been the case with our own sun.
Indeed. And, there's some evidence that there was more than one supernova that cooked off near the sun.
Yeah.
That seeded it once, and then it was reseeded after a good bit of formation had happened.
And that would support the idea that, and we know that stars in general are not isolated. They form in collections, associations, clusters. That our sun probably formed in such an environment so it would have siblings, brothers and sisters.
But we've had 4 billion years of going around the Milky Way at different velocities, and who knows where those siblings are.
Yeah, it's like you have brothers and sisters, but they had 50 years to go anywhere they want in the world. And then you woke up from a coma, let's say, after 50 years.
How do you find them?
How do you find them? Well, you do DNA matching.
Right.
So you got to go to every person in the world and sample their DNA and compare it to yours.
Right.
So it's going to take a while.
It's going to take a bit.
And that's what we do. We sample the DNA of stars by looking at their detailed composition through spectral analysis and compare it to our sun. And we haven't found yet an exact match, but we're still looking.
And we've found some close matches now.
Yeah, but not
an exact match.
Yeah, so we know we haven't found our brother or sister, but we're still looking.
We're still looking.
Now, the next interesting item that popped up recently is stuff about particle physics. So we're going to get in a little bit of a particle physics mode here. And it's results from a detector known as microboon, as you can see there in the title. What microboon did was look at different types of neutrinos. Now, what we call the standard model of particle physics, this described things like electrons and protons and neutrons. It's been around for several decades now, how we understand how the different particles work on the scale of atoms and so on. That within this theoretical framework, there are 3 types of neutrinos, which we mentioned already today. These are objects that have a mass, which we didn't know until a couple decades ago. 20 years ago, roughly. They have a little tiny amount of mass, so therefore there's gravity associated with them. And they interact very weakly with the weak force, as we call it. And these neutrinos, there's one associated with each of the what we call leptons, so an electron. So there's an electron neutrino. The muon, which is really a heavy version of the electron. So it's called the muon neutrino. And then there's the tau particle, which is an even heavier version. And we have the tau neutrino. And so these are like, if you like, 3 generations or 3 families of neutrinos. And there are no more. And if there are, that kind of that would change the standard model of particle physics. But that doesn't mean people don't look for things that don't match the standard model. And we're dying for looking at discrepancies because that may point to new physics that we didn't know existed, and we'd have to change the standard model. And so what people have been looking for is a 4th type of neutrino. And this type of neutrino is known as a sterile neutrino. And the reason why it's called sterile is because it doesn't interact via the weak force. It only interacts because it has mass via gravity.
So it wouldn't be associated with any of the leptons you mentioned, the electron.
Exactly, be on its own.
Yeah.
And there are some theoretical arguments you can make that show that they should exist, but then there are many theories, many ideas that people have that in some cases they exist for that particular idea of thinking, in other cases it doesn't. And so we just don't know. So you want to go out and look, do these sterile type neutrinos exist? Now, one of the things that's directly relevant here is that if you have a mass, even though it's very tiny per particle, there could be quadrillions and quadrillions of these things floating around in our galaxy and throughout the universe. If you have something that has a mass, but it has no other force associated with it, no electromagnetic force, no weak nuclear force or anything like that, it's the perfect candidate for the dark matter.
Yep.
That would explain why it wouldn't emit light like ordinary matter does, or absorb light or reflect
scatter
light.
it or anything else.
It's just gravity, and that's what we need. So it's been up there in the list of candidates for dark matter particles for many years now as a possibility. But this recent experiment, if you want to go to the next slide, shows it, this microboon. You see here, is lowered down. It's a 170-ton detector, and it was run here at Fermilab, which is just outside of Chicago, to look for signature then of the sterile neutrino. And what they discovered was there's absolutely no evidence for it at all. So of course, you could always improve experiments. In fact, that's what we do in science, right? We take the best technology that we have available, run an experiment, see a null detection, no detection, in other words. Well, maybe we're not just sensitive enough. So let's put together a better experiment to see if we can detect something. So you just kind of keep going to the next generation of detector, hoping that you see something, of course. It's not so exciting when you have a null detection, but in some cases it is.
Right.
It depends on the circumstance. In this case, there was no detection of a sterile neutrino, which means there's no evidence for going against the standard theory of particle physics, the standard model, which is unfortunate because we know probably if the dark matter is some type of subatomic particle, it's an add-on to the standard model, and therefore it would change things, right? We need to change the model itself to explain it. So they're going to run the experiment, of course, again, and it's going to be a better, more sensitive experiment. They're going to use other things besides what they used here, like they're going to take advantage of the DUNE project, which is the underground neutrino experiment that's going to be running very soon in South Dakota, not too far from us. And we'll see what happens in that case, to see if they can produce some of these sterile neutrinos.
One of the answers for possible non-detection with a neutrino experiment is you run it for longer.
Right.
Because the bigger your container, as you're seeing here on this picture, gives you more surface area, if you will, more volume for a neutrino to interact. But the longer you run it, the more time you have for a neutrino to interact.
Yeah, so there's 2 things you look at. Number one is the one thing you said, time, let it run longer. And the second thing is you make it more massive, so increase the tonnage. So instead of 170 tons, let's make it 500 or 1,000
or
a kiloton or something, right? And that's the sort of game you play, right? And the idea is you might say, okay, well, how can you detect something that only has gravity and yet doesn't interact? Well, eventually the neutrino itself could make a direct head-on collision, essentially, with a known particle.
And that would release energy, which would be detected.
And the result of that collision can be detected. But it's very, very rare. And the more mass you have, the increases the probability of some collision, or the more longer time you wait, as you suggested, the more the chance of a collision is going to occur.
Yeah. Neutrino detection is a big game of hurry up and wait.
Yeah, it's like, if you want an analogy, if you don't, not quite sure about that, imagine you're in I don't know, you went to a hall to a dance,
Uh-huh.
and it's near the end of the night. And everybody's essentially, almost everybody's gone. There are just a few scattered people walking around, just a few. And you need to use the bathroom. And it's dark, you're starting to shut down the lights and stuff, and the washroom's on the other side of the room from where you're at. And you just walk across the room. What's the chance of running into somebody? Well, if there's hardly anybody there, the chance is pretty low.
Right.
But if you went there 2 hours earlier when the dance floor was packed, chances are really great you're going to run into somebody.
Mm-hmm.
That's kind of like what's happening here.
Or in the time space, if you cross the room 100 times, your chances increase.
Yes, exactly. And so there are things you can do to increase your odds of a detection, and that's the game we play in all of this.
Yeah.
But so far, as of now, no detection of this fourth type of neutrino, which is interesting.
Indeed. Well, there's a lot of non-detections for the supposed dark matter particle that have happened recently.
Yeah, and it's a good thing. People are running experiments. They're getting money to support these type of experiments, so that's a plus. The other thing is, at some point in the future, if we don't detect the dark matter particle, and it's been maybe 10 years from now, we've done all the experiments, we might have to go back to the drawing board, as they say, and reevaluate our ideas of, is it really truly a subatomic particle, or is it something else that we missed?
Right. Does it require a correction to general relativity or something else?
Something is up. Anyways. So the final thing I wanted to mention is kind of off topic a little bit, but I thought this was a cool, interesting article. It was a study that was done from archaeological evidence obtained in Britain recently, of the evidence for fire use by humans.
Nice.
Now the evidence, and I could have showed you a bunch of slides about it, but we're running out of time here rapidly. But the evidence, which has been peer-reviewed and published in Nature, so it's a top journal in the world, is that humans have used fire, have controlled fire, for over 400,000 years now. So this pushes back a lot further our ideas of when we thought we were using fire.
That goes beyond the time limit, the time frame of modern humans.
Yeah.
Homo sapiens, as a matter of fact.
Yeah. You see evidence of, like different flints that were broken off that you can use to strike against rocks that create sparks to make fire happen. And there's evidence even of areas where they dug up. We can actually see location where there was a pit where they made the fire itself. You see evidence of that. So it's all controlled fire, the use of fire to cook food and probably even to do other things as well. Well, stay warm, of course.
Right.
Burning wood and stuff. But it's really amazing when you think about it. I mean, humans have been using and controlling fire then, for probably, who knows? You just based our history on what we find.
Right.
Right? What about the pieces of evidence that showed they were using it 600,000 years ago or 700,000 years ago?
Maybe out there waiting.
So out there waiting, you just got to dig up the right spot, right, in the world to find evidence of that. So yeah, the use of fire by humans has been around for many, many, many years now. So it's kind of cool when you think about it.
Right.
There's such a gap in our knowledge of the early history of eventually what turns into humans.
Right. Well, you said it right there. History. We've only been writing for 7,000 years.
Yeah.
So, what was going on before writing happened?
Yeah,
because that's hit or miss.
Yeah, and you'd wonder how much buried evidence is out there that if we only knew where to look to find this stuff, right? That would be able to figure out what happened, like 1 million years ago, and how did human species evolve on this planet. And if you compare it to the age of the Earth, this is the interesting thing. We're talking 400,000 years and thinks that's cool. The Earth has been around for 4.5 billion years. That's such a small fraction of the lifetime of the history of the Earth itself. You're just barely scratching the surface.
1/10,000th.
It's amazing when you think about that. So we've been around for almost nothing compared to how long the Earth's been here.
It's great stuff. And
in terms of geological time.
Yeah, just you got to get curious and you got to go looking for things.
But one thing you can do is to try to uncover the history of humans. And one way to do that, of course, is to go to higher education. Don't be afraid to go to university. Don't be afraid to learn new things, even if you think you're too old. Nobody's too old. As long as you're breathing and your heart's beating, right?
You can learn something.
You can learn something, and there's lots of things now with the internet for everybody to use. It's easy. You don't have to dig through encyclopedias or go buy them at the store or whatever. You go online, and there's all kinds of things out there. Use that information.
Right.
And learn about things. Come to the University of North Dakota. Take classes. Get your degrees. Go off and explore the unknown.
That's
what I say.
Absolutely.
Now, our next podcast will be next Tuesday. That's January the 13th. We leave a quote at the end of every podcast. Today, I decided to use a poem by Alfred Lord Tennyson, and it's in the In Memoriam. And it's about really related to geological time, how things are not static, they change. Even though that change may occur compared to our lifetimes over a long time scale.
Yeah.
Over the life of the age of the earth, things do change.
Yeah.
So here's the poem. There rolls the deep where grew the tree. O earth, what changes hast thou seen? There where the long street roars hath been the stillness of the central sea. The hills are shadows, and they flow from form to form, and nothing stands. They melt like mists, the solid lands. Like clouds they shape themselves and go. But in my spirit will I dwell, and dream my dream, and hold it true. For through my lips may breathe a dew. I cannot think the thing farewell.
Nice. That's a good one.
You like that?
I like that one.
Anyways, folks, if you liked our podcast, please remember to give us a thumbs up. Subscribe if you haven't subscribed. And we will see you again.
See you next week.
And Happy New Year.
Happy New Year, folks. Y'all have a great one.